I hopefully had a nice break, got a little snacky snack, got to use the bathroom, and excuse me, are ready to learn more about atmosphere stuff. I know, I sure am. And so, oh, by the way, I hope y'all like my Nintendo 64 hat. I chose this instead of one of my wigs. I asked my wife, should I wear one of my wigs for the video? And she was like, absolutely not. Maybe one of these days. Anyways, so imposter Miss Green is going to join once again. All right, so let's head back to our guided notes here. Okay, so we talked about albedo, our factor 3. Cool beans. The beans, they're cool. Oh no, the echo's back. I hate it. I hate it. I want to just go away. All right. So as we go down, we run into our talking about the tilt of the earth and how that is the singular reason why we have seasons, not because Earth is necessarily closer to the sun in any part of its orbit. It's all because of that tilt, right? So if the northern hemisphere is tilted towards the sun, we're experiencing summer, while the southern hemisphere is experiencing the opposite season, which would be winter in that case. As we are rotating around the sun, and we end up having our tilt away from the sun, and so the northern pole is facing away from the sun, the northern hemisphere is experiencing winter, and then the bottom half of the Earth is going to be experiencing summer, right? Hopefully that makes sense, right? If we have an axis that is tilted one way or the other, it's effectively putting one hemisphere out of the direct sunlight, right? And then pushing the other hemisphere into the sunlight. Okay, so hopefully that makes sense in terms of having opposite seasons in the northern and southern hemisphere. All right, so as we go down, let's talk about Earth's rotation and the Coriolis effect. Sounds like a spell, something exciting. All right, so in the northern hemisphere, that's where we're at, in case you're unaware. You should have like one of those maps, like you are here. Okay, so like, yeah, like somewhere between A and B in this diagram to the right. Large air masses generally appear to curve clockwise. And in the southern hemisphere, they appear to curve counterclockwise. Interesting, interesting indeed. So this curving pattern is a result of Earth's rotation in an eastward direction as winds move above the surface. Excuse me. And so the apparent curvature of an object traveling long distances on Earth is known as the Coriolis effect. Okay, and so the next part that I'm going to be reading might be a little kind of fuzzy. Keep in mind that I will go ahead and show you like a short little clip. How meta is that? A YouTube video of a YouTube video. Oh, I'm excited. A clip about the Coriolis effect and why it causes the curviness that it does. Okay. Okay, there we are. On a global scale, this effect produces steady, reliable wind patterns, such as the trade winds and mid-latitude westerlies, which sounds made up, but I promise it's not. Ocean currents also experience the Coriolis effect and curve clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. Okay, we have equal and opposite happening in our two different hemispheres there. Okay, same thing with our seasons. So imagine you are in space with an oxygen supply, looking down at the North Pole, so the center of your field of view. I feel like that's like a choose for your elf character in D&D. As the Earth spins on its axis, the North Pole is moving much slower than the equator because it's a much smaller area. Okay, and so we look at that diagram again on the right-hand side where it has point A, point B, and it's showing that rotation. We can see the latitude line near the North Pole, aka point A is going along a much smaller diameter circle, right? And so that's a smaller track, and therefore it's not going to take as long as the equator will in making that full revolution. And so I'll show you the video, but essentially, depending on where you are on Earth, because of the sphere-like nature, more of a geode shape of the Earth, we are going to be able to say, all right, if we are somewhere in a very high northern latitude versus the equator, we're actually going to be technically spinning faster near the top, right? Because it's not taking as long to completely make a revolution or a rotation as it would near the center of the Earth, because the center of the Earth is thick, T's into infinity, right? The center of Earth is thick. And so it takes a much longer time for that point B to make that same revolution back to its original spot. Okay. I think I just described everything in this next one. So that will definitely be re-emphasized in the video. Okay. So both examples show a clockwise to the right curve according to the point of origination, right? And so the effect is seen in the southern hemisphere with objects appearing to curve counterclockwise, so to the left. So according to the direction they came from. Okay. So large masses of air moving long distances, like Earth's atmospheric convection cells, are influenced by the Coriolis effect. And so we'll talk more about these convection cells. Basically, all it is air being pushed up from the surface of Earth and then coming back down at various latitudes. That's also going to be part of creating climate that we see across the Earth, because these different types of convection cells are going to be rising and falling with precipitation and different sort of temperature of air. And so that's going to affect sort of what's happening on our land masses as well. This is seen in the world's prevailing winds. So the convection cells are seen in the prevailing winds. The 6 major wind belts, so those are those convection cells, formed by the 6 convection cells. There you go. All curve clockwise in the northern hemisphere and counterclockwise in the southern. Okay, awesome. We have a pattern here. Everything in the northern hemisphere is clockwise, and everything in the southern is counterclockwise. Easy peasy, lemon squeezy. So you think. And so the winds on either side of the equator are the northeast and southeast trade winds from 30 to 60 degrees, or the westerlies. So at the north and south pole, or the polar easterlies, winds are always named for the direction they come from. So east versus west. Okay. And so is this the video? Yeah, this is the video. So let me say pause. Let me say new share. Let me make sure you have the sound on for this guy. Amazing. Cool. So let's go ahead and make this guy full screen.
If you've ever watched the news during a hurricane or wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the northern hemisphere, they spin counterclockwise. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise.
What? Didn't we just learn that it's clockwise in the northern hemisphere and counterclockwise in the southern? Why is it switched? Let's find out more.
Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis Effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas, and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator.
By the way, I think I got that mixed up where I was saying that the pole is moving faster than the equator. It's going to be the equator is moving faster than the pole. So corrections corner, you're welcome.
That means that the paper airplane is spinning faster as well. And when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high-pressure air surrounding the center, or eye, of a storm is constantly rushing toward the low-pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
All right. So you may be asking, why is it that this video just contradicted what Miss Green said? Let me explain. All right. So imposter Miss Green is going to bring up her whiteboard. All right. So let's talk about storms, baby. Okay. So when we are talking about our Coriolis effect, I feel like I spell it different every time I try to write it. We are just talking about, movement, wind, water, fire, earth, all trying to defend against the Fire Nation. It's late, y'all. It's like 11 p.m. So please forgive me. I am so tired. So movement of wind, water, based on the rotation of the Earth. I'll say Earth. And so I'm going to put a little note here without pressure. Okay. And so hopefully this will make sense in just a moment. Okay. So when we're talking about just the Coriolis effect in general, we're moving faster at the equator, at the thickest part, and slower at the poles. Okay. And so technically, if everything was moving at the same speed, if you were to have a magical paper airplane, maybe a magical empty monster can, because I know my people, and you throw it, you know, depending on if you're in the northern or southern hemisphere, you throw it towards the pole, it would continue straight, right? Because we're moving fast at the equator, we're moving fast, you know, near the pole. And so basically that momentum is going to continue straight. But because of that difference of speed, as the video stated, we're moving much slower at the poles. And so what that means is our paper airplane is whizzing because of the fast speed at the equator. But by the time the pole is able to catch up, right, it is already at a different position than where that equator starting point was. Okay, and that's the cause of that deflection, right? It's because the Earth is rotating, and so by the time it goes to land, the original point that it should have landed is already long gone. Okay, and so this movement, because of that speed difference, when we look at the Earth, I'm so good at drawing. And so we have our northern hemisphere and our southern. Okay, and just like the video stated, when we throw something towards the poles, we're going to have deflection. Okay, and the reason why we have deflection in the directions that we do is because the Earth, both northern and southern hemisphere, are moving in the same direction, right? And so the direction that the Earth is rotating is going to be in, if you're looking down at it, it's like is it clockwise? I think it's clockwise. So if we're spinning this way, okay, what's going to happen is instead of going straight, we are going to deflect to the right, right? And then if we're looking down and throwing in the southern hemisphere towards the pole, we are going to be deflecting to the left, right? And so as a result, this means that when we have water movement or wind movement in the northern hemisphere, we are going to have wind/water move clockwise. Okay, because then that same thing that is possibly being moved is deflected again to the right, again to the right. And so that's creating that clockwise motion. And so the southern hemisphere is going to be the opposite, right? Because things are being deflected to the left, we are going to have our wind and water move counterclockwise. And fun fact, in the UK, they call it anti-clockwise. And I don't know how I feel about it. All right. And so because we're deflecting to the left, you can see that counterclockwise movement happening. Once we are talking about storms, right, we now have to take in consideration pressure, under pressure. Okay. And so pressure systems are always going to move from high to low pressure. And so to give you a good example, if you remember from bio, maybe chemistry, I'm sorry if that's triggering for some of y'all talking about other science classes. But if we're talking about a solution, so we're talking about a solution. So a solution is just stuff that is diluted within water. Okay, it's aqueous, so it's stuff suspended in water. You have a beaker, which this is totally a beaker, and this green is an artiste. Maybe I'll put some measurement lines over there. This is so ugly, I'm sorry. And let's say that we have a semi-permeable layer straight down the middle. So semi meaning partially, permeable meaning passable, right? And so some stuff can get through, and specifically the some stuff is going to be our solute, okay, our solute. So that's going to be the stuff that's dissolved in that water. And so if we have like a few of our pieces of solute over yonder, but then on this side of the layer, we have a lot. Like they have an apartheid over there. And so just kind of the nature of the world, nature of nature, things want to kind of achieve that stability. And so, for instance, if you remember from chemistry, sorry, once again, and we're looking at the periodic table, all of those elements are trying to achieve noble gas status. Noble gases are the popular girls, okay? And that's because they have complete stability. They have their octet completely complete in their outermost shell or layer. known as our valence shell, right? And so because of that, and they feel that stability, they are unreactive. They're unbothered, okay? And so all elements are going to react accordingly to achieve that noble gas status, okay? And so same thing when we're talking about a solution with solutes in it. This system is going to want to try and achieve stability. How it does that is through equilibrium. And so just like the word sounds, equilibrium, all parts are going to be equal, okay? And so what that means is when we have this semi-permeable layer that only allows the bits of dissolved stuff in the water to pass through, we're going to see a movement from the highly concentrated side over to the less concentrated side. So we have the high concentration side versus our low concentrated side. Okay, and it's going to continue sort of that passage through that layer until we're going to have equal parts on both sides, right? And so that's the same idea behind pressure systems within our atmosphere, okay? And so usually we have, when we have a high pressured center, okay, that means all of the wind, the water, depending on what we're looking at, is going to be moving towards this high pressure center, right? And so when we have movement towards, right, that is where we're going to see our classic patterns of deflection due to the Coriolis effect, okay? So we have air coming inwards, wait, it's outwards. This green is, okay, so it goes from high till low. Okay, so high to low, high to low, high, low, hello, high to low. Okay, and so when we have this movement, we are going to see our deflection accordingly, right? So in the northern hemisphere, we are going to see that deflection to the right, deflection to the right, deflection to the right, deflection to the right, and so on, right? And so this looks like our typical clockwise movement as described in the Coriolis effect. Okay. So when we are then looking at a high pressure system in the southern hemisphere, okay, same thing, we're going to have, that is not how you spell high. I don't even know what that was. Was that Swedish? Okay, so high pressure system. We are going to have that same movement outwards from high to low. High to low. But this is going to be our southern hemisphere. Okay, and so that means things are being deflected to the left. So to the left, to the left, to the left, to the left, to the left. And so that is going to create our counter or anti-clockwise pattern, which is also described in the Coriolis effect. I just realized these are like red light, green light colors or reggae colors, however, however you want to look at it. Okay, so that's our high pressure systems. When we then look at low pressure systems, and so low pressure systems are the ones that are really, really dangerous, i.e. you know them as hurricanes in the northern hemisphere, and they're called cyclones in the southern hemisphere. And the difference between them is simply the direction in which they spin. But they're the same phenomenon that happens, you know, due to this low pressure system. And so now let's switch things up. When we have a low pressure system, going back to this idea of what's happening within a solution that has uneven distribution of solutes, our low pressure system is going to have high pressure, whatever it is we're talking about. So if it's wind, water, we have the high moving into the low. Okay. And so when we have our northern hemisphere, we are going to still deflect to the right. And so we're moving in, we're deflecting to the right, deflecting to the right, deflecting to the right, to the right, to the right. Is this one having an arrow? To the right. Okay. So now this is creating that counter clockwise direction. Okay. So that's why we have that sort of interesting, it sounded like a contradiction at first. How is it that everything, according to the Coriolis effect, is moving one way in this particular hemisphere, but the other way in the same hemisphere when it comes to storms? And this is why, is that movement from high to low pressure. And so now in the southern hemisphere, when we have a low pressure system, so this is going to be our low. And we have the same thing happening, things moving from high to low. And things in the southern hemisphere deflects to the left. Okay. We end up having to the left, to the left, to the left. I sound like Beyonce, but like spoken word. To the left, to the left. Everything you own is in a box to the left. Okay. And so that's how we end up getting our clockwise. Okay. So again, this is high pressure systems over yonder is going to be our low pressure system. And so what's important to know is the change in direction is going to denote where it's at in the world. So if you're given a picture, say on your notes, you want to see what's happening on the tails of the storm and how it's moving inwards. Is the way it's moving inwards to create that cinnamon roll into the eye of the storm, is that going clockwise or counterclockwise? Okay. And so if it's going counterclockwise, that is referred to as a hurricane, and it occurs in the northern hemisphere, right? And so a lot of y'all have experience with hurricanes and you know them well. And so if you were to look at a picture of a storm and you see that cinnamon roll happening in a clockwise fashion, we know that's going to be a cyclone. Okay, so it's the same exact phenomenon. Again, it's just happening in the southern hemisphere. How do we know what's happening in the southern hemisphere? Is because this is moving clockwise. All right, so hopefully I did not lose some of y'all to the storm / to all this information I'm kind of loading you up with. But hopefully that kind of clears things up and really kind of cements these concepts, right? So at first glance, it was confusing why we have clockwise and counter happening in the same hemisphere, and this is why. So let's go back to our notes. Let's have imposter Miss Green leave because the echo is so distracting. Let's get out of here. Atmosphere stuff. Okay, and so we do have some of these practice questions. I think we got through all of them except this last one in block 5. So if you threw a paper airplane north from Texas, what is the most likely place it would land? Okay. If all points on Earth were traveling at the same speed, it would land in Nebraska, which is directly north of Texas. But because we have this difference of speeds, i.e. the middle of the Earth, the thickest part of the Earth is moving faster than the poles, okay, we're going to have that deflection happening. So that deflection in the northern hemisphere is to the right. And so we're going to land in Delaware. And so for this next little part underneath that question, an object moving from the equator south would move to the blank. So we're assuming we're facing south. And if we're facing south, anything that we throw towards the pole is deflecting to the left. Okay. So let's look at these practice questions on the right side column. So which of the following statements about the Coriolis effect is incorrect? So the Coriolis effect causes objects to be deflected to the right in the northern hemisphere. That's correct. So let's go on to the next option. The Coriolis effect causes objects to be deflected clockwise in the southern hemisphere. So if we think about how we are throwing things and deflecting to the left, that's counterclockwise. Let's keep that in mind. Global winds are not affected by the Coriolis effect. The heck they do. So that one is actually definitely incorrect. D, the Coriolis effect is caused by the rotation of the Earth. It's true. E, the different rotation speeds of Earth at different latitudes causes the deflection of traveling objects. That is true. So if we go back to the Coriolis effect causes objects to be deflected clockwise in the southern hemisphere. If we go back to our diagram that Miss Green just made us, we see that objects deflect to the left, and so that should be creating counterclockwise things to move. But if we're, I guess, talking about storms, it would be clockwise in the southern hemisphere. So I would say C would be the best answer. That global winds are not affected by the Coriolis effect, because that is untrue, I'm pretty sure. Yeah. So coming on down, underneath that question, the Coriolis effect and prevailing winds contribute to the formation of gyres in the oceans. Which direction do these gyres flow in the northern hemisphere? That is going to be clockwise. So storms in the northern hemisphere, low pressure systems, are going to move counterclockwise, but everything else that is not governed by these low pressure systems is going clockwise. Okay. If we move down to this picture of a hurricane, okay, identify the hurricane of the hurricane pictures below. So we just want to identify, is it northern or southern? Again, we kind of want to look at where that cinnamon roll tight bun is going towards. So if we look at the edges of the storm, aka the tails of the storm, we see that we kind of have our tails moving into our little swirl. And because we are moving to the left, creating a counterclockwise situation, okay, that is going to be happening in the northern hemisphere. So again, when we are talking about just wind, water movement in general, that has nothing to do with low pressure systems, everything in the northern hemisphere is moving clockwise. But once we are talking about low pressure systems, i.e. storm systems, i.e. hurricanes, in the northern hemisphere, it's fine, I'm just hearing tapping. I'm gonna hurry up and finish this video so I can hide elsewhere. Okay. So in the northern, I swear if it's one of y'all trolling me, you'd be so mad. Y'all found out where I live again. All right. So once we are in the northern hemisphere and we have that low pressure system where the tails are going to be our high pressure moving inwards towards the low pressure, that deflection of those winds to the right, is going to cause that counterclockwise motion, right? And so storms in the northern hemisphere, counterclockwise, everything else clockwise. So I think that was it for that. I am going to leave. Please wish me luck and hopefully I won't be dead. Anyways, love y'all. Have a good weekend. Be safe, socially distance, wear your mask, be safe, get vaccinated if you can, and don't get arrested. Love y'all. See you next week. Bye. Ooh.